All right, you guys, we only have about 2 more sections left in this class, so hang in there with me. We're going to talk about 12.4 today. If I lectured over this whole section, I think this lecture would probably be like 45 minutes, and I don't think you're going to stick with me through that long of a video. So I need you to read the section. That's going to be quite important for this. And so I've assumed you've read this section. What I want to do is I just want to talk about a couple things, okay? So the things that we need to talk about is this idea, 2 things. This idea of what we call an exponential. I don't know if I spelled that right. I think so. Random variable. And what you saw in the book, and they do a good job of kind of discussing this idea of an exponential random variable. And to me, I mean, I'm what you call a pure mathematician, so I'm not an applied mathematician, but I really kind of like how E is kind of an interesting function because it comes up so much. It comes up in population growth, it comes up in, we've seen it already when we've talked about present value or future value of money or population or whatever we're dealing with. So this exponential random variable, right, that is a random variable. So X is an exponential, I'm gonna be a little lazy here, random variable if it has an exponential density function. Okay, and so the exponential density function, which they talked about in the book, the exponential density function that we have that goes along with this random variable, okay, is f of x equals k e to the negative kx. So we're still talking about continuous random variables just like we were before. We're just basically looking at, okay, if this continuous random variable has a function, a density function, probability density function of this type right here, we give it a special name, okay? So we call it an exponential random variable. So this is my exponential density function. Oh, I got a little too excited there and wrote a little bit here. So my exponential, this is my function here, and this is for x greater than or equal to 0. And then they have, so this is if it has that density function. Also, they kind of prove this. This is a theorem, and you should look through the proof of this. The expected value, this is actually a pretty cool proof that they show you. There's a little bit with limits there that you have to be kind of careful of that maybe you don't believe, and that's on page 572. I'm kind of looking at it right now. If you look at, like, there's a little equation with the called 3 there as b goes to infinity. You should look at that. You should maybe put in some numbers into your calculator and see if you agree that when b goes to infinity, the claim that they make that it goes to 0, that term goes to 0, is true. If you have questions about why that's true, please email me. I'd be happy to send you a little explanation of why. I have a feeling I'm not going to get any emails about that. But if you look through their argument on page 572, they actually show you that the expected value, this is pretty cool, of this random variable is 1 over k, and we'll talk about how we find k. My variance then of this random variable is 1 over k squared. So they show that this is true for any random variable that has probability density functions such as this guy right here. Okay, so just wanted to kind of get that out of the way. I'll let you kind of look through. They do a pretty good job of talking about that in the book. And I'll let you look through that. So let's do an example. That's what I really want to do. So the length, this is our example here. So the length between, I don't know how to spell length apparently, between calls received by some switchboard, I before E except after C, I think. By a switchboard is an exponential random variable. And they were talking in your book how this is true. Like if you, like waiting times can be modeled a lot by exponential variables, which I thought was kind of an interesting thing. So this is what we know. We also know something else. The average length the average length of time between calls is 20 seconds. So that information is actually going to be quite important. Okay, it's 20 seconds. Okay, so here's the question. If a call has just been received, what we want to find is what is the probability what is the probability that no calls are received in the next 30 seconds? All right, so there's a lot of stuff that we need to kind of unpack here and figure out what this is talking about. All right, so here's what we got. We got a random variable, right? So what I like to do is I like to think about, well, what does this mean? My random variable is, you grab any call, and what is our outcome? The length between those two calls, right? So the average length of time between calls. So if I look at any two calls, my random variable is that average length of time between those two, okay? So what I know, something that I do know, is that the average length between calls is 20 seconds. So that right there, that yellow part there, what that implies to us is that my expected value, if I just take any length, right, is going to be 20. And how is that going to help us? Because if I look back here, what do I know? Because what I need to find, right, is I need to find my probability. Whoa, settle down. My goodness. Sorry about that. I need to find my probability density function here, okay? So my probability density function, or exponential density function, is going to help me find my probability, and that's what I need to find. So to be able to find that, I need to find k. Okay. So what I know then is if this is 20, remember, for an exponential random variable, right? And what else? I'm going to write this down really quick so I kind of know what I'm doing. This is k, right, e to the negative kx, and I need to find that k. Well, if I know that e to the or my expected value is 20, then I can solve this. And what does this imply? This implies then just flip both sides. That implies that k is 1/20th. Okay, you can do that as long as there isn't any addition or subtraction, just two fractions equal. Flip both sides, we know that k is 1/20. All right, so this is good news. Let me erase a little bit of this because I'm going to need some room here. All right, so what I want to do then, I need to find my exponential density function. So my exponential density function then in this case is 1/20 e to the negative 1/20x. Okay, that is I know we call it the exponential density function. Think of it as your probability density function for this specific type of random variable. Okay, same thing. So this problem is a little bit difficult. What is the probability that no calls are received in the next 30 seconds? So when would I not get, so what does that mean? If I don't have calls in the next 30 seconds, remember what x is here. This is the length of time between any two calls. So if this length of time is less than 30 seconds, then that doesn't satisfy what I'm asking for here. So what I want is I want to know, when is this random variable greater than 30 seconds? Because if there are no calls received in the next 30 seconds, that means my next call could be like 31 seconds, 32 seconds. I wouldn't have any calls between the next 30 seconds. I hope that makes sense. I know that's a little bit strange there. I'm gonna need some room here, so I'm gonna get rid of this stuff right here. Hopefully you got that in your notes already. Okay, so how are we going to do this? Well, we know how to do this, right? We want to go from what? There's no bounds really on x. So the length between, if a call was just received until the next call, hypothetically, could be from 30 to infinity. I just don't want any calls between 0 and 30 because that would say that I had a call within the next 30 seconds, right? And I want the probability that I do not have a call. All right, you guys. So I'm going to rewrite this with a limit because we've been doing this for a while. I'm going to go ahead and skip one quick step here. I'm going to take the antiderivative of this. I'm just going to leave the 120. How do I take the antiderivative of this guy? I rewrite it, right? And then I need to divide by the exponent of this. Not the exponent, by the derivative of the exponent. So what is the derivative of the exponent here? It's just a negative 1/20. So I'll deal with this in a minute. And then that 30 stays. And what did I replace that infinity with? I replaced that infinity with the b, because we know that the fundamental theorem of calculus has no idea what to do with infinity. So we have to replace it with a variable. Now this is pretty cool. These guys are going to cancel here. 1/20 divided by 1/20 is 1. And then I have a negative. Now, what does a negative exponent do, right? It puts that guy in the bottom. So I'm going to have a negative of e to the 1/20 times b minus negative 1 over, so I just took this negative and put it in the numerator, e to the, well, I'm going to have 30 times 1/20, whoops, which is 30 divided by 20. And then I'm going to get out my calculator. So I hope that makes sense. And there's another way to do this, and I'll kind of show you another way to do this also that they show you in the book. But this was just the first way that I did it. And this becomes a plus, right? And so what happens to this guy right here? This guy's going to go to 0 because the denominator is getting quite large. And I'm going to take 1 divided by e to the 30 divided by 20 in my calculator. I think I got that right. And here's what I get. I get 0.22313. So 22, let's say 31. Okay. So 2231. So again, what does that mean? Do you understand what that means? There's a 22.31% chance that we have no calls in the next 30 seconds, right? Or another way of thinking that is all of my calls are going to, I have a 22% chance that the next call is 30 seconds or greater away from the last call. Okay, I hope that makes sense. If you don't like how we're doing this with the 30 to infinity, one thing that you can do that they show you in the book, and I actually really like this, if you don't like doing all of this, I just actually didn't think to do it right now, you could do 1 minus 0 to 30 of the 1/20, 1 over 20 e to the negative 1 over 20x. And the reason we can do that is, remember that if I integrate this whole thing from 0 to infinity, it's going to equal 1. So if I integrate from 0 to 30 plus 30 to infinity, that would equal 1. So if I just subtract this guy from both sides, this is what I'm going to get. Another way of thinking that is, there's a 100% chance that my calls are going to be between either 0 and 30 or 30 to infinity, right? So I'm going to take that 100% and I'm going to subtract, well, what's the probability that some of those calls are in the next 30 seconds, 0 to 30? Well, then if I subtract that probability, I'm left with the probability that they're more than 30. So I hope that makes sense. I know that's a little bit weird, can be kind of weird sometimes, but okay, so that's the big idea with the exponential density functions. And you need to make sure that you look at the example, like look at example 1 and then look at example 2. They do a good job of showing you examples on how to do this. So make sure you look over those. If you have questions on those, you need to let me know. All right, the next part of this section then, let's clear this guy out. This is going to seem a little hard, but it's actually not too bad. Okay, so the next part of this section that you looked at, or that I'm going to let you read about, is this idea of a normal random variable. Okay, and some of this stuff is not proven for you, and that's okay, but a normal random variable, so it's an exponential variable, okay, that has, so a normal random variable is going to have what we call the normal density function. Maybe I should say X is a normal random variable. I can't spell normal. Random variable if it has, now this is a little crazy, normal density function is what we call this. This is an exponential density function. It's just a little bit funky. Just looks a little bit different. Here's what this is. We have f of x equals, now this is going to be a little bit strange, but I have 1 over sigma. That's just going to represent, we've seen this before, that's your standard deviation, all over the square root of 2 pi times e raised to, hang with me here, a negative of x minus what we call this fancy m. I know it looks like a cursive u, but it's actually like a fancy m. We call it mu, quantity squared, all over 2 sigma squared. Oh, you should go scare some people with that. And I don't really like, it doesn't look like that's a variable to me, or an exponent, but that's my exponent for e. Okay, where we have a couple things going on here, where my expected value, okay, is just going to be that mu, or that fancy u. It's just a Greek letter. It looks like u, but it's really an m. And then my variance here, which we would expect this to be true, right? Because we know our standard deviation is the square root of my variance. So my variance is just the square, right? And then of course, what is, that's my standard deviation. It's always been the square root of the variance. So this is what we call a normal random variable. And there's some interesting things that they show you about this. Some things that are kind of interesting about this, it has inflection points at mu plus. If you kind of look at the graph of this, okay, this guy right here, if this was my data, this would be my mu. I would have inflection points. This is kind of cool stuff at mu minus sigma and at mu plus sigma. And if you've had any statistics, that should start kind of making sense to you. Mu, that's my average, that's my peak, right, of how this stuff is normally distributed. This is what we mean by normal distributed function, is when I get a nice peak like this. And then what this standard deviation kind of does for us, or the sigma, is it kind of tells us like how steep or how sharp that peak is. Okay, so that's what we mean by a normal density function. And I know that can be a little bit confusing. Okay, so the problem with this function right here is if I were to try and take the antiderivative of it, or to integrate this, I won't be able to, not with the methods that we have. If you ignore all of these symbols and stuff and just think of this basically as e to the x squared with some other constants, we don't know how to do that. So we're going to do this a bit of a different way. So again, I'm going to let you read the book on some of this, just because this lecture is getting a little bit long. But the other thing, right, that you looked at was this idea of a standard normal variable. And the standard normal variable that we're talking about here, because it's a standard normal variable, we actually use a capital Z to talk about the standard normal variable, okay? When we have the capital Z, we're going to assume, this is a little crazy, but that my average is 0, and we can just take our data and maybe shift it over so that this is true, and I have a standard deviation of 1, okay? So I have my mean. I'm going to kind of take maybe something that was just a normal random variable, and I'm going to kind of shift it over so that I'm guaranteed that my mu is 0 and my sigma is 1. And that what that gives us is a standard normal curve, okay? Where would this curve go? Well, at 0, right, I would kind of come up. I would have my mu at 0. That's what I want. I want it at 0. And then my standard deviation of 1. So at -1, oh, my curve is a little weird, and 1, that's where my inflection points occur. Okay, so the thing about this is, if I were to look at, and so what would my standard density function then look like in this case? And a lot of times we don't use x. We're actually going to say that this is little z, just to really hit home that this is a standard normal curve. Well, if you go back to that equation that we did before and let sigma be 1, and I'm going to let mu be 0, then what you get, and I'm going to replace the x with a z. I put little lines through my z's so that I can tell them from a 2. I'm making my 2 a little more cursive there. What we get if we replace, so look at what I've just done here, and I said I wasn't going to go through this very often, but this guy became a 1, this became a 1, so that's where the 1/2 came from. This mu became a 0, and then x I'm just replacing with a z. So this is what we call a standard normal variable, where this is basically our probability density function. So for instance, if I wanted the probability that my standard normal variable lies between a and b, right, that's a capital Z, what would I have to integrate? I would have to integrate this thing right here. And this is a problem. We don't know how to integrate this. We can't do parts, right? Because I don't have anything to really do parts with. This is something true in mathematics, that we don't know how to integrate e to the z squared. We know that you can integrate it because it's continuous, but we don't know how to actually take the integral of it. So what we do, remember what this is. This is just the area, right? Under the curve, maybe from A to B, under this curve right here from A to B. So what we do instead, whoops, sorry about that. What we do instead is we say, okay, I'm going to define something. I'm going to define this function A, and capital A, okay, oh, whoops, I need that to be a little z. I'm defining this function. This function is going to be capital A of little z, and what that's going to give me, that's going to be the area under the curve from 0 to little z, okay? Area under the curve from 0 to little z, which means I'm just taking the probability, right? That's what area is. It's just the probability from 0 to little z. And likewise, if I'm going to take the area of, let's say, a negative z, because sometimes we could do that. We could have a negative. I would go from negative little z, right? I would do, of my capital Z's look a little bit weird, to 0. Also, notice what this is going to imply. We're symmetric about this line right here. So if I'm going up to z right here, from 0 to z, notice if I take a negative z, that is exactly the same. So one other thing that's important about this is that a of little z is exactly the same as a of the opposite of little z. Man, this lecture is going to be a little longer. I told you it wasn't going to be, but it is. I hope that kind of makes sense. Man, this is a long lecture. So what I would like to do, I think I am going to stop right here, let you have this, and then I'm going to start part 2. And in part 2, what we're going to talk about is how do we actually find these, okay? And what we're going to need, because we don't know how to actually evaluate this, what we're going to need is we're going to need a table. And this table is going to be in the back of your book. And I will, in the second part, I will do some examples just focused on the standard normal variable. All right, so come back for more.